All right, I think I'll get started then if everyone is happy and ready. So welcome everyone to this webinar covering the Atacama Cosmology Telescope Data Release 6 lensing products and notebooks. I'm Blake Sherwin. I'm going to start us off today with an overview of the ACT-DR6 lensing analysis and a quick summary of products that will be discussed in more detail by subsequent speakers. For many of you, this will be a reminder because a lot of what I'll discuss has been covered in these papers that are listed here. So the Atacama Cosmology Telescope, unfortunately, is a former telescope. It's no longer operating. It was dismantled last year, as we're now focusing our experimental efforts more on Simon's Observatory. But fortunately, there's a huge amount of great data that's now saved on disk that the ACT collaboration is working to analyze right now. The CMB data set that these lensing results are based on, these lensing products are based on, is the ACT-DR6 CMB map set, which is an amazing set of CMB maps for the purposes of lensing, right? And it has everything going for it. First of all, it has high arc-minute resolution. It covers, a lot of the sky, 18,000 square degrees in temperature and in polarization, and it has very low noise, right? With a median depth of 10 microkelvin arc-minute, but you can see the distribution of noise levels in microkelvin arc minutes over the sky in this plot. So in short, it has 10 times more statistical power than the previous ACT cosmology data release, which is a big step forward for ACT. And this is great for lensing. Now, the ACT lensing group built an analysis pipeline to measure lensing from these CMB maps. And this lensing analysis pipeline is based on a curved sky quadratic estimator. The way this works, this estimator, is that it looks for new lensing-induced correlations between different formerly independent modes of the CMB temperature and polarization. And so in this way, using this curved sky quadratic estimator, we're able to go from maps of the CMB temperature and polarization to maps of the gravitational lensing, the lensing potential or the lensing convergence, which probes the mass in projection. Okay, and so without further ado, let me show one of our key products, the ACT-DR6 CMB lensing mass map. What's shown here is the gravitational lensing convergence, which is directly proportional to the density of mass. Now you can see our lensing mass map covers, is probing the mass distribution in projection over a quarter of the sky. And it's filtered using a Wiener filter so that you're really seeing signal-dominated scales, and you're really seeing the dark matter distribution and projection by eye. So most of the contributions here, given the lensing redshift kernel, come from around redshift 1 to 2. This is a very high-fidelity map, and to make the statement more quantitative, let me show a plot of the noise power spectrum as a function of multiple, which you can see for ACT-DR6 here in red, and you can compare that to previous lensing maps, shown here in blue, and to the lensing signal in black. And the conclusion is there's a wide range of scales up to L of 200 over which we're really imaging the lensing, really imaging the projected mass and projected dark matter. So I will refer you to Matt Madavacharo's presentation for some of the details of the released lensing map products. We hope that this lensing mass map will be really, really useful to the community, because the community will be able to begin a campaign of cross-correlations of this ACT lensing mass map with other tracers. And this will be interesting for cosmology, for astrophysics in many different ways. For example, it'll allow you to make precise measurements of the growth of structure as a function of redshift using such cross-correlations. Part of the reason this map will be so useful is that it has great overlap with several optical and infrared surveys, including the Dark Energy Survey and SDSS, as shown in this overlap plot. I'm just going to show one example for a high signal-to-noise cross-correlation with ACT-DR6 lensing maps, just to show you the power of this lensing data set. And the example will be the ACT lensing unwise galaxy correlation that was published late last year, led by Garrett Farn. I'm not going to be able to do justice to all the really interesting cosmology constraints in that paper that you should take a look at, but I'm just going to show the cross spectra of our ACT-DR6 lensing map with unwise galaxies in the blue sample coming from redshift 0.6 and the green sample coming from redshift 1.1. And the takeaway for the purposes of this presentation is just there's a ton of signal to noise, around SNR of 60 in both of these redshift bins. So this is a very powerful lensing map for cross correlations that hopefully many of you will use. And you should also please look out for some other ACT cross correlations that are coming up with DESI and DES. And please also see Frank Chu's and Joshua Kim's notebook presentations on some details of these cross correlations. Now, there are some subtleties to be aware of when you're using our ACT lensing map for cross correlations and more generally. The first one is that the local normalization of this lensing map is not absolutely perfect. It relies on theory. If you care about high precision normalizations, you should use simulations. This will be discussed later by Joshua Kim. Another subtlety is that we're using a cross correlation based estimator, so you need to be a little careful when you're using theory errors. Sims are a little bit more reliable to get error bars. There are also some subtleties to do with foreground treatment, but Matt will discuss these shortly. Let me now turn to a reminder of our ACT lensing power spectrum results. So here in red, you can see the ACT CMB lensing power spectrum measurements. And you can compare them with a prediction for this lensing power spectrum based on Planck 2018 CMB anisotropies and lambda CDM. And so what you can see is that we find excellent agreement. Our lensing power spectrum measurements are in excellent agreement with this early time CMB prediction. The great agreement of what we measure with what you predict based on early time CMB and lambda CDM also is reflected in the parameter constraints that we obtain. So you can see here in blue is the combination of sigma 8 and omega matter that we constrain. The best constrained parameter combination is this S8 CMB lens combination written here. And a key result is that our lensing measurements are not low, and they're in very good agreement with, again, the early time CMB predictions based on Planck shown here, for example, in orange. You can get tighter constraints from CMB lensing alone if you combine our ACT lensing measurements with the Planck lensing power spectra, appropriately including the covariance and the joint likelihood. Here are the constraints that you obtain, or the best constrained parameter combination is written here. And you can get tighter constraints still if you combine ACT lensing and Planck lensing with BAO, giving you a very nice result of sigma 8 equals, a constraint of 0.812 plus or minus 0.013. Again, in great agreement with what you predict based on early time CMB. So great agreement with the predictions. Now, this likelihood, of course, is public. There are some subtleties that you should be aware of if you want to reproduce these sorts of plots or use this likelihood for your own purposes. One thing that you should be aware of is that if you're running lensing-only constraints, there are some assumptions that go into these lensing-only constraints. For example, some priors that are assumed, but these are generally quite conservative and weak and safe to use. A good thing is that there are negligible correlations of our lensing band powers with the sort of current 2-point analyses. In the future, this may change. And this will be discussed, sort of subtleties to do with the likelihood will be discussed in more detail by Matt Madavacharo and Karen Perez Sarmiento in later parts of this webinar. And on that note, let me hand over to Matt Madavacharo, who will discuss in more detail our released products.
Thanks, Blake. So I'm going to spend the next 7 or 8 minutes discussing the released products. So all of these will be are public either on NASA Lambda or on NERSC. So on the next slide, first I want to discuss the likelihood and change. So we really encourage people to use our public likelihood and to use the change that we provided. The likelihood for the CMB lensing auto spectrum from DR6 is available as a standalone Python package on the PyPy repository. You can just pip install it. You can also go to the GitHub and get the code directly. The standalone version can be used with inputs from any Boltzmann solver. You can just put in your theory prediction for the CMB lensing auto spectrum, and it'll give you a log-like value back. When you use Boltzmann solvers, we recommend certain accuracy settings specifically for CAM, and you should compare those accuracy settings with what you get from class. You typically need higher accuracy in the Boltzmann solver prediction than has been standard with Planck, for example. I should also point out that the version of the likelihood that matches our published paper is from earlier this year. It's version 1.2, so please make sure that you use that latest version. Once you install this package, you can use it with popular sampling inference frameworks like Cobaya and Cosmosys. This has been done by several analyses in the past. It's very easy to integrate them into Cobaya and Cosmosys in particular. We provide several variants of the likelihood, the data vectors that go into this. So there's a version that only includes the ACT lensing autopower spectrum. And there's also a version that combines with the Planck CMB lensing auto spectrum, properly accounting for the covariance between them because they share a common sky area. And we have variants that have the baseline multipole range, which is the multipole range that we used, that we decided on before unblinding. Overall, we recommend using the combination of ACT and Planck because that gives you the full signal to noise available with CMB lensing measurements at this point. There's also an extended version that goes to a larger range of multipoles, specifically higher multipoles that we deemed was safe to use after unblinding. So if you have models that are looking at smaller scale physics, then you can use the extended version. An important point to mention is that there is a flag in the likelihood, the lens-only flag that you should set to false when you're combining your likelihood with primary CMB 2-point measurements, say from Planck or ACT. This is because this accounts for changes in the normalization as the CMB spectrum changes in the chain. This is important to incorporate, and it affects your uncertainties at around a 10% level. So please make sure to use that flag if you're combining with CMB 2-point power spectra. Finally, the GitHub itself provides a link to the chains from our papers if you want to use our public chains and show plots of our posteriors in your papers. On the next slide, the next point to discuss here is the release of the lensing maps themselves. These are all linked. All these paths that are shown here are linked from the NASA Lambda entry. The full set of map products that includes all of our simulations are in this particular NERSC directory that you can also access through this web URL. In particular, we provide many variants of the lensing maps. So this includes lensing maps that have only polarization data or are null maps that are constructed from differences of CMB maps. These are extremely useful for doing null and consistency tests. So typically, if you want to do a cross-correlation analysis, you want to use these null maps to make sure that you get a null signal before you unblind your analysis. The directory also includes a link to around 400 Gaussian lensing convergence simulations with associated lensing reconstructions. So these can be used to calculate a transfer function, as I'll talk about in a bit, and also to construct covariance matrices for your analysis. On the next slide, I want to talk a little bit about the usable scales and cluster locations in the maps. The maps themselves are provided as spherical harmonics that you can project to your desired pixelization. For example, if you want to use the HealPix pixelization, you can use the HealPipe package to project the ALMs to a map. Or if you want to use rectangular pixels, you can use the pixel package to project them to that pixelization. The mask itself is provided in the HealPix format. I want to point out that galaxy cluster location. So we discussed this in Madhaveshwar et al. The fact that in this lensing map that we provided, the galaxy cluster locations themselves were not reliably reconstructed. This is due to subtleties associated with the quadratic estimator that discussed in this paper by Hu, Dedeo, and Veo from 2007. We recommend avoiding stacking on galaxy clusters themselves. In particular, the SC clusters from ACT, these had special treatment applied to them. So for example, you can see here that if you stack on the lensing map at the location of the ACT SC clusters, you'll get a signal that doesn't really make a lot of sense. And this is expected given the treatment of the quadratic estimator. So we encourage you to avoid those locations particularly. We provide a mask of SC clusters that you can exclude from your stack. This, of course, shouldn't stop you from generally using the lensing map for cross-correlations with galaxy samples and galaxy groups. Those are totally fine to cross-correlate with. The non-zero modes in this map are from multipoles of 2 to 3,000. However, modes with multipoles less than 40 may not be necessarily reliable. So we've seen some instability in our null test, even though the null test formally passed. So you should be a little bit careful about using larger scale modes than LF40. And the specific maximum multipole that you use for your analysis should be determined for your particular cross-correlation analysis from foreground bias assessments, which I'll talk about in the next slide, and also any theory modeling constraints that you might have. So let's talk about foreground simulation, the foreground simulations that are provided here. So we provide quote unquote lensing reconstructions that are made from foreground only simulations. So, as many of you might be aware, CMB lensing maps are reconstructed from millimeter frequency maps that include non-Gaussian contributions from foregrounds such as the SC effect and CIB. So we've used the WebSky suite of non-Gaussian extragalactic simulations to assess how well our foreground mitigation strategies are working. And we made these simulations public. So what we recommend you do is that for any galaxy sample of that you might be working with, you take the WebSky Halo catalog and you build an HOD out of them. And then you cross-correlate that galaxy catalog that you developed from the WebSky Halo catalog with our foreground-only lensing reconstructions to check that you get a cross-spectrum that is null or zero. So an example of this is shown here from Farron et al. That did this for the unwise galaxies. So you typically want to see a null spectrum when you cross-correlate these foreground-only lensing reconstructions with the HOD that's made, as shown here. So given the mitigation methods that we've implemented, we expect you to find a null result, but if you don't, you should let us know, because we haven't seen so far any galaxy sample where foreground biases can be detected, which is a testament to the work that we've done to implement algorithms that mitigate these foreground biases. And on the next page, on the next slide is the last subtlety here, which you'll hear from Joshua Kim in detail. There's going to be a notebook that presents this. Any correlation function or cross spectrum that you do with our lensing maps may need up to a few % correction, depending on the mass that you use. This is because the normalization that we apply to the mass applies for the entire footprint. But if you have an analysis that is done on a region that is a significant subset of that footprint, then the normalization changes a little bit. And so we provided these simulated reconstructions and their input simulations that you can use to characterize this transfer function. So I've shown this schematically here on the right. Whatever function that you apply to your galaxy sample in cross-correlation with the CMB lensing reconstruction, this might be a correlation function, this might be a Fourier space cross-spectrum. You're going to apply that to the reconstructed simulation, cross-correlated with the true input theory, the true input Gaussian convergence with the particular mass that you use, and you want to average this over the sims that we provide and then divide by the theory prediction based on the cosmology that we've specified in our simulations. That'll give you a transfer function that you can divide out of your analysis. And we don't expect this to be more than a couple of % at most. In most cases, it's much less than 1%. And so this transfer function should always be estimated and applied to your data vector. Otherwise, you could be off by a couple %. So that's all I wanted to point out about the subtleties in the products. I'm going to now pass to Zach Atkins, who is going to tell us about generalities associated with the ACT-DR6 notebooks.
Great. Thanks, Matt. So I'm Zach Atkins. I'm a graduate student at Princeton University. So the rest of the webinar will be devoted to walking through a series of notebooks that help the community and the users interact with our lensing products and apply them to their own analyses. Before we do that, I just wanted to take a quick step back and sort of give a broader overview to the ACT data release environment in the notebooks in particular. So if we start by going to the NASA Lambda page and we navigate to the ACT section of that website, and in particular the Advanced ACT tab, we'll get to this page where we see all of our DR6 products that have been released so far. So for instance, our Compton Y map and our lensing maps, our lensing likelihood. And if we keep scrolling down, we'll get to this section, which links some notebooks that we released as part of our DR4 and DR5 data release. So we had a lot of success and positive feedback from the community related to these notebooks, and we wanted to replicate that program for DR6. Very briefly, these notebooks for DR4 and DR5 deal a bit more with sort of the lower level tools you might use to interact with any of our data products. So like Matt mentioned, the Pixel library, So if you're looking for more of a sort of general introduction to how to interact with ACT products, this would be a nice place to start. For DR6 in particular, you'll want to navigate to the ACT collaboration GitHub, and then within that repository, you'll look for the DR6 notebooks repository in particular, where we are compiling these DR6 notebooks. These notebooks really target working with our DR6 products, not as much the lower level tools for interacting and working in Pixel in general, although they do overview what's necessary to within Pixel to work with our DR6 products. Another difference with respect to the DR4 and DR5 notebooks is we worked especially hard here to make the learning curve for interacting with these products as shallow as possible. So for instance, if I open one of these notebooks, which you'll see very soon, you'll note at the top of the notebook is a button that says open in Colab. So if I follow that button, I'll immediately be taken to a Google Colab environment. And this environment will handle all of our package management, as well as the downloading of data without us having to do anything. So you don't need to worry about managing your own environment or downloading data directly to your laptop. So it should be very easy for users to get started working with the DR6 products. This comes with a few limitations. So the Colab environment does not have nearly the same computational resources that you'd find on a cluster or even on your laptop. So many of the computations that you'll do as you walk through these notebooks, you'll find to be a bit slower than you might expect. And that's okay. So the purpose of these notebooks is really to get you started working with our products and making sure that you understand how you would perform an analysis. But for actually performing your own analysis, you'll want to adapt the code that's presented here and port that over to your own cluster where you'll be able to perform your analysis much faster. So without further ado, I'll pass it over to Frank, who will be walking through the notebook that you see here.
Thank you, Zach. Hello, everyone. I'm Frank. I'm a postdoc at the University of Cambridge. And in this notebook, I'll walk you through how to load these ACT products, namely the ACT DR6 lensing map. And in doing so, I will show you an example of how to visually see the correlation with large-scale structures, such as the CIB. I will not show you here how to do a quantitative analysis in a cross correlation and default that to future notebooks. So the first thing you do is to load the general packages that we are going to use. So we have Pixel, which is mentioned by Matt and Zach. These are the map loading, manipulating, and analysis for these rectangular coordinates that's used for ACT. You can do any pixelization you want, so that's why we also have HillPy and AstroPy for some other operations. So the products I'll be loading today consists of an external data set, the cosmic infrared background, which is the large-scale structure I'll be cross-correlating with our lensing map. I'll be loading our baseline analysis mask used for lensing products, fiducial lensing power spectrum, and the reconstruction noise for DR6 levels to filter our lensing maps and show the real signal-dominated scales. And finally, last but not least, the lensing map, which is stored in spherical harmonics. So once you load all the products, the first thing I'll show you here is the analysis mask that we have been using through our analysis. So this is stored, as Matt said, in HillPix coordinates, and we can just load that with HillPy to show the footprint. So this is a binary mask, which is apodized on the edges with a 3-degree cosine apodization, and it extends from declination of -60 to 20, covering 9,400 square degrees of the sky. Before plotting the lensing map and associative filtering, as an aside, I'll just show you the external tracers we use. So here, this is the product taken from Planck. So this is a 545 gigahertz cosmic infrared background, which covers a similar redshift to our lensing map and show a lot of correlation. And this is the map of this CIB. Again, here, this is the mask, the galaxy or galaxy's mask, and this is a full sky map of these dusty star emissions that we can load and process so that they are in rectangular coordinates and save them as spherical harmonics. So now back to our main product, or lensing map. So this is the convergence stored in spherical harmonics. If you just naively plot it, you will show the scales as well, which are noise dominated, and you'll be quite noisy. So we want to apply some sort of filtering. And for that, we apply this Wiener filter, where we construct this filter based on a fiducial signal and the signal plus the reconstruction noise. So this will really enhance the signal dominating scales. We can apply these to our kappa field and plot the resulting map here. So because we already filtered out the noisy scales, what you're seeing here are the real signal, the lenses at a particular direction in the sky. So in this color scheme, bright regions consist in regions where there's a higher density of dark matter in projection, and black regions are low density. You can see that there is some artifacts, some features leaking outside the mask, and that's just due to the Fourier space filtering we applied, but they do not affect the analysis, so you can mask them if you want. We can apply the same sort of filtering to do an apples-to-apples comparison with the external tracer, the CIB. So we can do that in these cells here and plot the resulting map. Again, with the same kind of color schemes. And here what you're seeing is regions of overdensity of this luminous matter, and the dark regions are the underdensities. Probably there is you can see already a very high correspondence between them, but it would be nice to just show the CIB as contours and overplot that on our lensing map. And this is what we do in the cells here to process the CIB map into contours. And again, we can then just overplot that on top of our lensing map. And you can see that there is a very high correspondence between the CIB, the luminous matter, and the underlying dark matter distribution. So you can see that better by zooming in a small patch of the sky. And this is a very good visual correspondence confirming that our mass map is really measuring the dark matter in projection. And now I just hand over to Joshua, who will tell you more about the transfer function. Thank you.
Yeah, thanks, Frank, for that. 1 second. All right, so hi everyone, my name is Joshua Kim, and I'm a grad student at the University of Pennsylvania. And I'll be talking today about how we compute and generate this ACT DR6 lensing transfer function. So a couple of points I want to make before we get started with this notebook is that for the purpose of this notebook, we'll be working with the angular power spectrum regime, but the same sort of logic will apply if you compute real space 2-point correlation functions, as Matt mentioned, and that this is a transfer function that's already on top of a variant that's already been applied to all of the ACT lensing products and described in Q et al., where we apply sort of this similar transfer function, multi-Carlow norm correction, onto the ACT DR6 lensing auto spectrum and all of the data products due to non-idealities, due to misnormalizations with anisotropic noise filtering and the cross-correlation-based estimator, but that's already been accounted for. This notebook will describe a secondary multiplicative correction when you, for example, use the lensing map for a cross-correlation analysis. And you have a different set of maps, different set of masks, and the mask geometry differs. So we're doing a secondary correction in the order of a couple percent to account for that. Yep, so let's get started. These two cells here will just set up the environment for us to use. The data products we'll be using for this notebook include, of course, the ACT DR613 analysis mask. We will use a secondary mask. In this example, we are using the Galaxy mask for the DES Year 3 BAO analysis. So that's downloaded right here. And then we're going to need the simulations. So as Matt and Blake mentioned, a theory prediction may be misnormalized, so we want to be using a simulation-based estimate. The ACT DR6 lensing suite contains 400 pairs of input lensing potentials used to create 400 Gaussian reconstruction, lensing reconstruction simulations. So these are paired by indices, and there are 400 of them. And we're not going to download all 400 for the purpose of this notebook, but there are 400 of them, and we recommend anyone doing a formal cross-correlation analysis to use the full suite as necessary. So we download the sims, download all of the data products here, label them as forward. The Python packages we'll be using for this notebook include NumPy, HealPy, which allows us to use the HealPix format for our maps and masks. PyMaster, since we're working with angular power spectra, we use the Nemaster code, which incorporates binning, mask coupling, mode coupling to compute angular power spectra of masked fields, and we have Pixel as well. So we install that in this cell, and we import them all here. This may take a couple minutes to download everything, install, etc. So that's up. And since Nemaster incorporates binning, we define some constants in this cell very quickly to specify our binning scheme for our output. So here, this is not really necessary. I plot the masks here. So this one is the DES Year 3 BAO mask that we'll be using, and then this is a different view of the ACT DR6 lensing analysis mask that Frank just showed. So these two we'll be using for the transfer function computation that we'll show in this notebook. One thing is that we take the Galaxy mask here and then we make it binary just to make the calculation a little bit more simple. And then also make sure that the resolutions of the masks that you import are of the same, are equivalent. So I think I had to downgrade one of these to make sure they match an inside resolution. There's that. These are some helper functions to help us bin a fiducial spectrum that doesn't require us to run a full Nemaster mode decoupling algorithm. So we do that. We just write these functions here. We'll use them later on. And the definition of transfer function is defined right here, where we have in the numerator an average over the iteration of simulations, where we use Nemaster to compute the angular cross spectra between the reconstructed lensing convergence kappa hat and a field X, which could refer to either the input lensing convergence used to lens the reconstruction simulations, or a correlated Gaussian galaxy field that you can draw from the input lensing convergence. There's a function here that does that. For the purpose of this notebook, we'll be using X equals the input lensing convergence just for simplicity. So that also means that the external denominator, which is going to be the Nemaster binned theory prediction for CL kappa kappa, the lensing auto spectrum, is going to be a denominator. And what's important is that this transfer function, we're going to have a measurement for CL kappa G, CL kappa kappa. We're going to be dividing that measurement by the transfer function to scale it up to what we expect from the theory, and then use the transfer function divided result into our likelihood for a data vector. And again, we're just going to be computing with X equals kappa over here. So for the numerator, we set up the following line of code. Of course, Google Co-op limits our resources. We won't be iterating through all the 400 simulations. We'll be only going through sims 1 through 10. So we set that up here. This function defines the sort of sets everything up for the iteration and iterates through all of the sims. We'll be calling a helper function that we define here, which actually runs Nemaster to compute the individual cross spectra for each of the sim pairs. One quick caveat is that the ACT-DR6 lensing analysis mask is actually applied at the level of the CMB temperature field. So when we do the reconstruction with a pair of CMB temperature fields, this effectively applies the analysis mask squared onto the lensing reconstruction map. So we actually provide K-mask squared to Nemaster and tell Nemaster to take K-mask squared into account when we do this computation. So that's just a small detail that is specific to the ACT-DR6 lensing analysis mask, because it is non-binary, it is apodized, and there'll be a couple % difference if we don't specify this mask squared parameter. So that's the numerator, and we ask the Colab environment to run the function, do the iterations. And for 10 simulations in this Colab environment, it took me 20 to 30 minutes. So we recommend that if you're running on the full suite of 400 simulations, you might want to move this code over to a cluster where it can operate this much faster. So 10 pairs took about 20 to 30 minutes for this notebook, just a heads up. Denominator is a lot more simple. We're just binning a fiducial theory spectrum using the master. We download the theory prediction right here and bin it using our helper functions defined previously right here. And we compute everything, compute the mean of the iterations for the numerator, and then divide that by the denominator, save that to disk, and that's our transfer function. So let's, I guess before we look at the results, I'll quickly just mention that you don't necessarily need a master to compute the transfer function. You could do it per L, but you would have to apply what is called a W factor correction to take into account the fraction to sky that is lost due to masking. So this will account for the mask, and you can compute the W factor for your specific mask geometry for whatever mask you provide, whether it's this one used in the notebook or whatever one you choose. This function for pixel will compute this W factor. So let's look at how the transfer function looks like. First, we'll plot the denominator and numerator separately, and they look quite similar. There's small deviations from 200 to 400, L's of 200 to 400, but that's expected. And then let's look at their quotient, which is the transfer function right here. And we see that the transfer function is pretty much in agreement with 1, showing that it's not a big transfer function. Our geometry, our mask geometries were very similar. And we should expect that the transfer function may deviate from 1 more and more if the mask geometries of the overlap, if the overlap is very different from just the ACT lensing footprint. So here, there's no obvious scale dependence for this transfer function. It fluctuates on the order of 1 or 2%. And the error bars, we're plotting errors in the mean here, are quite large because we've only iterated through 10 sims. They should surely shrink when you iterate over the full suite of 400 simulations. And yes, that is how you would compute this transfer function. And just to remind everybody, you take our measurements and divide by T of L to get the corrected power spectra to pass through likelihood. All right, I will pass it on to Karen, who will be talking about the lensing likelihood notebook. Thanks, everyone.
Thanks, Josh. Hello, everyone. Today, my name is Karen Perez Sarmiento, and I'm a grad student at the University of Pennsylvania. Today, I'll be talking about this notebook that shows us how to work with the ACT-DR6 lensing likelihood. So the ACT-DR6 likelihood contains a covariance matrix and the power spectrum to allow us to estimate cosmological parameters. To do this, we usually also need an MCMC library, and the one that we will be using here is Cobaya. Here we provide some documentation to Cobaya, for Cobaya if you want to get familiar with it. When doing MCMC, we usually have to sample the parameter space many times and generate a theoretical power spectrum also many times. Usually this is done using some sort of Boltzmann code, like class or CAM. However, in this notebook, we will use Cosmopower, which is a set of trained neural networks that speeds up the process of computing the theory power spectrum significantly. If you want to become more familiar with Cosmopower, again, we have here some links to the code and the paper. Now, one of the first things that we will do in this notebook will be to install the required libraries and the dependencies. Here we're installing Cosmopower, all of the dependencies, and then also Cobaya, which is our MCMC framework, and of course, the ACT-DR6 lensing likelihood, as well as the data products required to run it. Now, Cobaya requires 4 main components to do MCMC. It needs to have some settings for these 4 components. First, we have the likelihood. It needs to know which likelihoods to use to compute it. It needs to know about the parameters that will be sampled, derived, or fixed. So these are the cosmological parameters. It needs to know which theory code to use. Usually CAM or class. In our case, it will be Cosmopower. And it needs to know which sampling algorithm it will to use to do it. In our case, it'll be Markov chain Monte Carlo. So all the settings for all of these 4 components need to be passed to Cobaya via a settings file, a YAML file. So one of the next thing that we'll do in this notebook will be to download this YAML file over here. And then we will just make some minor modifications to it and explore and see what it looks like so that we can run it within this notebook. So first, let's look at the likelihood component. This is what the likelihood block of this YAML file looks like. We see that we're using the ACT-DR6 lensing likelihood, as well as the VAO likelihoods. And here we only need to make a minor modification. We need to point Cobaya to the right, to the path where the VAO likelihoods are installed. So that's what we do in this block. So that's good. Next, let's look at the parameter, the component with the parameters. So this is a dictionary that contains a list of cosmological parameters that we are sampling, deriving, or keeping fixed, as well as their values and their associated formulas or their priors and reference distributions. We don't need to change anything here, just wanted to highlight what that looks like. Next, let's look at the settings for the theory code that we're using here. So this is what the theory block looks like. We're using class ESC fast, which is the wrapper for Cosmopower. So we're using Cosmopower as to compute the theory power spectrum through MCMC. And next, finally, the other component that we need to look at is our sampler. We're using MCMC, and the only modification that we need to do, make from the original settings file is we're going to change this R-1 stop parameter from 0.01 to 0.1. And this is because we just want the chains to converge faster in this notebook. If you wanted to replicate the results in Madhavachettiar et al. 2023 paper, you would have to set this back to 0.01. Just as a side note, this R-1 stop parameter is just the tolerance for deciding when the chains have converged. So usually a smaller parameter means that the better convergence, but also means longer runtimes. With all of these modifications, and we are ready to save our changes and run the chains. Over here, this block is the one that actually this is where we are actually running the chains. We can see the output, what would come out if you were to run it. This takes about 26 minutes in this Google Colab notebook. we recommend that if you're planning to run this with the R-1 parameter of 0.01, or if you want to speed up the process a lot more, we recommend that you take the code from this notebook, make it into script, and run it in your personal computer or in a cluster. But this is already much faster than at the time that it would take if we had used CAM or class. So it's already pretty fast given the constraints of this notebook. In this notebook, we're also providing some code to help you plot the results from your chains. So here we have what the triangle plot for these chains look like, and we can also compare this to the results reported in Madhavachetter et al. 2023 paper. To do so, we first have to download the chains from that paper and overplot them over here. So we see that the contours are in pretty good agreement with each other. And if we had ran our MCMC with that R-1 parameter of 0.01, then we would have exactly replicated the contours. Finally, here we have some links to all the other DR6 notebooks, to the notebooks from past data releases, and then to the Pixel notebooks, which are notebooks that have some information that guide you through how to work and handle ACT maps with the Pixel library. Now I will pass it up. I'll pass it on to Matt, who will be moderating the Q&A. Thank you.
Thank you, Karen, and thank you to all the speakers and presenters. Yeah, we have around 10 minutes to take any questions that people want to ask. So I'll look out in the Q&A session in the panel. I'll give a few minutes for people to think of questions. I don't see any questions so far.
Zach has a question, it looks like.
Oh, Zach, please.
Not a question, but I'll just quickly add as well for anyone in the audience. We had a webinar yesterday as well that focused on the ACT YMAP release. And so if you were not able to attend that, or you want to refer back to this webinar as well, both of them were and are being recorded, and we'll distribute those publicly very soon.
Yes, and I'll also add, go check out our page on NASA Lambda with all the links to all the products, the bigger set of products on NERSC as well. Please make sure to always read the README files. Okay, I'll wait another 30 seconds to see if people have questions. If not, it looks like our presentations might have been very clear.
And obviously, feel free to email any one of us, right? If you think of something later, I'm sure we'd all be happy to answer questions.
Exactly. All right, great. We'll close off the webinar then. Thanks everyone for attending. Take care.